because he has been working in industry. Mr. Harsha Jaiswal is BTech in Electrical and Electronics Engineering from RGPV Bhopal, and he has also earned his Masters in Microsystem Engineering from OTH Germany. He has a good experience, work experience in different institutions, like maintenance engineer in Indian Army. He has worked for 4 years. Production and validation engineer. He has worked at Nevo Controls Private Limited Indore for 6+ years, and he has been working since last 5+ years as staff reliability and quality engineer at AMS Osram, Austria. So we welcome you, sir. All of us are eagerly waiting to hear to you, sir. It is
Yeah,
over to you,
thank you.
sir. Thank
Yeah,
you, sir.
thank you very much for a nice introduction. I wanted to introduce, but you did it already. Okay, so we will talk
Yeah,
about.
please, you can take it again if I missed out something, sir.
Okay, okay. So we will talk about product reliability. So how the reliability is achieved, what is the what we do in to achieve this reliability, and what are the things important for the product reliability. So I'm Harsha Jaiswal. I have a bachelor degree in electrical electronics engineering, master's degree in microsystem engineering from OTH Regensburg, Germany. And I have also experience from 4 year working in Indian Army as a maintenance engineer, and I work around 7 years in India for a instrumentation company as a electric. I actually work for multiple positions there. So, but product validation and production and in some part of R&D as well. And more than 5 years, I am working with IMS Osram as a staff engineer. So my mainly focus is about to handle the product reliability stuff. So may I know how many of you are already aware what is the wafer, what is how it is processed, what is the die, and what is the package, something? Or do you have any idea about the what is the semiconductor industry works?
If you know about it, please type Y in the chat box so that we can understand that yes.
Okay, so I just in the picture, just basic intro. In the picture, you see on the right hand side, it's a circular disc. It's called wafer, and wafer is also fabricated in the our fab. So this wafer has could have 1,000 devices, 5,000 devices, or maybe 100 devices, depend on the size. And in the left side, you see a package. It's called ceramic package. In the middle, you see a die is there. One of the die is from wafer. So this die, we cannot directly touch it to this. So this is the reason we have the package to take out the pin of this die outside. And how the package and die is connected, it's connected through the wires, and it's gold wire. You can't see, maybe you can, if you zoom your side, you can see this very tiny wires, which is 2 times thinner than our hair. And on the middle, you see the flip of this package, which is which is the pin grid array package. And similarly, we have all the different type of package, but we will not go into that. So the next about the introduction of reliability. So what is reliability? So I would say reliability is the for a device, reliability is ability to perform under a specified condition over time. Because how we can say the device is reliable, because it's working defined functionality under the specified time and the condition as well. So this is the reliability. And it is why it is so critical, because for the performance side, because to achieve this there are many combination of the material is involved, many processes are involved, because the maybe the device design, device size is also smaller. So all this combination we have to put together. So so that it becomes in the end reliable product. So this is the reason I would say it's very critical to achieve this reliability. And some other things, like what are the things influenced by of the reliability? Design, definitely the design will influence the reliability, because if the design is not good, how we will achieve the good product? And the material, and because as I said, different type of material is involved in this, like silicon, germanium. These are there for the die making, and for the package, it's a different, like plastic mold or ceramic or different type of. So the material is also very critical to choose, because it can also destroy or completely destroy the company reputation. And about the uses, it's also important. This is the reason we have the data sheet to tell or to inform the customer that, okay, these are the specified condition where you achieve the very good performance of the devices. So if you go through the data sheet, you will see all the information, how how the device should be used and what the functionality is that. Next slide. Just give me a minute. Okay. Okay, so about what is reliability ensure? So in reliability ensure long-term performance and quality. We will not talk about the short time, because short time maybe any product can work for short time, but we have to think for really long time, because these devices are can be used for different type of electronics where we need uh, for long many years as a use. And if I look for the definition, what is exactly the reliability? In the internet there are many definitions, but which I found which fit to this. So it's uh, uh, sorry. uh, okay. Okay, so if I say the what is the very good definition? So the very good definition is probability that device will perform the required function under a specified condition for a certain time period, because everything is defined here. What are the condition? What how long it will work, and what are the functional? And if I summarize this definition in one word, it's called survival rate, because the device should survive in the end. Then what we need to achieve a good reliable product. So the main work of reliability team is to develop hardware software for this, to test, to be able to test the device. Reliability stress execution. This is the second step, but let's go for the first step. So the hardware, we develop a hardware when, because everything is together, like we get a plan from the product engineer, okay, that this is our device and we have to qualify. And we have already a plan, what are the type of stress, what is the environmental condition, what type of the voltages, and what is the type of package we will have. So based on that, we develop hardware, so that because the we with these small devices we can't connect directly to the supply. So this is the reason we have to develop a board which is called HTOL, or a trace board. So on the bottom left, you see this is a type of HTOL board where we have I think 84 position per board, and each position this is a board for a QFN package. So this board is developed such a way that we can apply voltages. We can also monitor the performance of the device. Yep. And then reliability execution. So what is reliability execution? That once we have everything like hardware and software developed for this, so we have to load this board into the chamber. So this chamber is called stress chamber. So on the right hand side, you see a big chamber. This is one type of chamber, but we in the reliability we have different type of chamber for different type environmental stress. So this chamber is called HTOL and LTOL chamber. So there are two chambers. On the up there is a HTOL, and the low side there is a LTOL chamber. Means LTOL means low temperature and HTOL means high temperature operating lifetime. So where we load our board, we load our board and then we apply the right sequence of power on, and we monitor the device during the throughout the run. And then when we have this executed the environmental stress test, then we go for electrical testing. And why we need this electrical testing? To be able to know whether the device is passing or failing. Otherwise, there is no reason to do all this kind of things, because main reason is to know whether the device is survived or not. So, and this electrical test is always done pre and post stress. Because why in the pre? Because device is fresh, we did not apply any stress on it, so all the parameters are ideal in the condition. And why in the post? Because now we have applied the stress, so the parameter can shift. So we call it drift analysis, so parameter can go to the lower side or higher side. So this is the reason we have to apply electrical test as in the post as well. But there is also one thing, we don't apply electrical test in the end. So we always take care that to have the readout, electrical readout intermediate. Means, for example, if we have to run 1000-hour HTOL, then we have several readouts like 48-hour readout, then devices are passing or failing. Based on that, we have 168-hour readout, 500-hour, and last 1000-hour readout. And to achieve all this, what is the important main thing is planning, because planning is very important in this, because we have all these critical devices. If we don't have good planning, then we can't execute smoothly anything here. Okay, and why reliability matters in the semiconductor? There can be many reasons, but I listed some major three reasons. Uh, Cost of failure. If we don't take care about the reliability of our product, then it can cause a lot of cost for the company. Because if a part is failure in the market, then we have to recall it from the customer around the world. And it can also be a safety reason, because if the part is used where it comes to the life, it can also be a danger for some human life. So this is also safety risk. So this is also one. And second, application. So this part can be used different type of application: automotive, aerospace, medical, home appliances, everywhere. So wherever the part can be used for different type of application, and based on the application, we develop a part. And this is also very critical to achieve the reliability. And it's also really important that we provide very good part and reliable part for this, especially automotive, aerospace, and medical appliances. Because for example, a car, we in a car, I think around 2000, almost 2000 ICs are there to control all the system, like brake, clutch, indicator, light, everything. So if one part is failure, for example, you have to apply a brake, and the brake IC is not giving the indication to the system, then it will not do anything. So it can also risk of danger for the life. So this is the reason. These are the application where we really take care of the um, uh, two products which should be reliable throughout the lifetime. And the third most also affect the brand if we are not able to deliver very good parts to the customers. So this can also uh, uh, very bad effect to the brand, and this way we can lose the customers. And the next one, reliability. There are some key reliability lifespans. So like MTTF means mean time of failure. So what is it? So the average time of a component is expected to function before it fails. So the our device should function all these defined parameters within the range, within the specified condition, within certain time period. So it should function without without it fails. And why it matters? Because higher MTTF means larger devices, the larger device life and better reliability. And and this is also used to predict product lifetime and warranty to the customer. Because how we, whenever we buy a mobile, how for example Samsung, how the Samsung will say, okay, for 2-year warranty, no, nothing will happen, just use it. So because they have tested all the parts through the reliability, all the parameter, they did all the environmental testing, low temperature, high temperature. Otherwise, for example, one mobile is working in India, maybe we can use at 45 degree there, but one mobile can also work in Norway where we have minus temperature. So we have tested this part through the minus and high temperature as well. This is the reason they provide the guarantee warranty, that the part will, your mobile will work during this condition. And the second is fit rate. This is failure in time. So fit rate means the number of the devices expected failure per 1 billion devices during the hours of operation. So, and the fit can be calculated like 1 billion divided by the MTTF in hours. So there is a formula I did not mention here because then we need to go through all these equations and all, which is not relevant to this. And the third one is the tub curve. So this picture gives a explanation of a lifespan of a device. So in the beginning, you see the earlier failures. So this, what are the earlier failures? So the device, the earlier failure means infant mortality. So means here we screen out all the failures during the electrical testing, because, and this failure could be the poor material due to the manufacturing defects. So this, every time we have more failures during this early stage. And the second stage is called useful life. The middle section is useful life. So here very low fail and constant. Maybe if we have failed, it's always with one parameter or something. But we always take care that there should be no device and during this time period. And the last one is wear out. So wear out due to the aging of the device and material degradation, because maybe we are using this device for a very long time, 10 years, 20 years, then it's aging the device. And this can also happen that the device is failing. And this is called wear out failure. Um, okay. Uh, we have some reliability acceleration factor. We can also say the aging factors. So different aging factors can generate different failure mechanisms. So one is HTOL, as I mentioned earlier. So HTOL means high temperature operating lifetime. So means the device is stressed when it's biasing, means the voltages are applied, input signals are applied, and we also monitor the device functionality. The main aim of this HTL trace is um, to switch on all the transistors in the device, so so that we can see, okay, the live device is working. And depend on the qualification plan, uh, the temperature is set. For automotive is different, for consumer application it's a different. So but mostly it's used for 125 degree, maximum 1000 hour. And if we go above 1000 hour, it's for internal company check. It's called robustness validation. Second is LTOL. It's the same but with a low temperature. Uh, there are now, in the third point, we have THB, means temperature humidity bands, where we have temperature plus humidity and biasing. And the second one is TH, means temperature and humidity is there. And the third one is HAS, means highly accelerated stress test. And the last one, and the HAS is also used where we use biasing. And the last one, UHAS, means unbiased. So means where we don't have supply, but we have pressure and humidity. And all four tests can be is used for the to generate the galvanized corrosion in the package, so that in this way we are trying to put a moisture inside the package so that it can fail. But if the moisture, and this is also to check the reliability of package, if moisture goes in, means this device will fail during the electrical test, means our material of the package is not good. So we have to investigate further. Next, TC, it's called temperature cycling. So again, depend on the qualification plan. Different type of temperature conditions are applied. So, but mostly which are used like -40 85 degree, -40 125, -40 150, -55 150, and -65 160 degree. And what we generally do, so we place the part into the oven, and oven is programmed how many cycles we need to run for this temperature, low to high, low to high. And how many cycle is defined, generally it's for 1000 hour. And yeah, and then we do again after this trace, we have certain intermediate readouts, as I mentioned for the H2L. Then we check the device is passing or failing. And in the temperature cycling, what the mechanism, failure mechanism accelerate, like when we apply the temperature, so in the device there are two type of material. Now one is die, one is outer package. So there are two different material, right? So when we run the temperature cycle, means low to high, so this can also, if there is a fail between different two materials, so we try to check material mismatch between die and package. So this is the aim of this test. uh, Next is HTSL, so means high temperature storage lifetime, because sometime and this test, for example, we supply the part, and the parts are in the storage room of the customer. So this way we try to check how long the device can survive without it used. So how long we can store it. And the next one is PCON. It's called preconditioning. And this preconditioning, we simulate the solderability of the product. And this preconditioning contains three stages: temperature cycling, moisture soak, and bake. But it's not for 1000 hour. So we do 5 cycle of temperature cycling: -40, 160, 5 cycle, 5 time, then finish. And then moisture soak. And moisture soak is again comes from the qualification plan. So we have three category of moisture soak: MSL1, MSL2, MSL3. So for MSL1, we apply moisture soak 85 degree and 85% of relative humidity. MSL2, 85 degree and 60% of relative humidity. And MSL3, 30 degree, 60% of relative humidity. And why we have different MSL condition? Because all they have the different floor lifetime. So MSL1 has 168 hour. We apply moisture soak for 168 hour. And why? Because the condition is harsh, 85, 85. So it has unlimited lifetime, floor lifetime. We could say floor lifetime. For example, you have package on your hand, IC package on your hand, and you don't want to solder, so you can apply on the PCB. So anytime. So there is no limitation that you should solder it within 24 hours or within certain time period. So and the second MSL2, 85, 60 degree, and it has 4 week. We also apply moisture soak for 168 hour, but we have only 4 weeks lifetime. Why we have four weeks lifetime? Because our stress condition was less compared to MSL1. And the third one is MSL3, where we apply 30 degree, 60 percent relative humidity. And relative humidity we apply for 192 hours. And it has only 168-hour floor lifetime. Means once the customer has this part, he has to use in the application within 168 hour. Next one is PTC. So as we know TC, so this is PTC. PTC stands for power temperature cycling. So in addition, here we apply the power as well and the power temperature cycling. So power is not here steady state. So we switch on, switch off, switch on, switch off. So we define the process uh, through the with the product qualification engineers that how the switching on and off should take place. So what should be the time and on and off. If you want to if you want to learn about this acceleration factors, you can look to the JEDEC standards. You will see the more detail on it. Uh, Next is semiconductor failure mechanism. As we have seen in earlier slides, so the failure acceleration factors. So here we see the failure mechanism. Because of that stress condition, we try to generate this kind of failures. So electromigration and galvanic corrosion. So this apply only for where we apply biased means H2L, THB and Hast condition. And hot carrier injection is also for LTOL and HTOL. And a time dependent dielectric breakdown. This is for HTSL because with storage condition, we check the dielectric material strength, that how long it will survive. And then negative bias temperature instability. So here we apply the negative supply to the device to be able to check the negative bias temperature instability. And thermal and mechanical stress. So thermal stress it comes from temperature cycling, and mechanical stress is also comes from temperature cycling. But there are two type of temperature cycling: temperature shock and temperature cycling. So what is the difference between them? So the temperature cycling, one chamber can go from low to high, and it takes smooth ramp to go from low to high or high to low. But what is the mechanical shock here? We also call thermal mechanical shock. So here the device see the sudden temperature change. So this is the reason we call it a shock for the device, because here we don't give a smooth ramp up or ramp down to change of temperature. And to achieve this, we have different type of equipment. We call environmental stress testing equipments. So the left one is a bake oven where we apply HTSL. On the bottom one is for temperature cycling, and the upper one is for HAST, height humidity, because here we have humidity inside. Yeah, and for if we talk about the reliability testing overview, so why it helps. And reliability testing is done, as I mentioned earlier as well, that reliability testing is done pre and post apply before the environmental stress to the device. It helps us to predict and improve the lifetime of the device. And what type of the reliability testing we do? So ALT means accelerated lifetime, burn-in, which is also called HTOL, which we have seen, and environmental testing, which we had to talk like temperature cycling, HAST, THB. One thing I forgot to mention in this slide, what is the difference between HAST and THB. So the difference is for harsh is for short time because the condition is harsh. 130 degree, 110 degree, 85 percent humidity, or second is 130 degree and 85 degree. And for THB, it's always 85. This is the reason they both type of stress helps to generate the same type of failure mechanism, but harsh is more harsh because it's the conditions. Uh, and here we had a talk, and these two pictures give you some idea about how we do the electrical testing. So on the right side, you see there is an electrical tester, and on the left side, you see we call it board load board, where we load the board. But in this load board, you just see only one device, possibility to load only one device. So similarly, we have many different load boards where we have possibility to load multiple devices at a time and test at the same time. Maybe on the right side, the big picture you see there is a green, this green area. This is also a load board, and I can here we have multiple position testability in this, and uh, this electrical test machine is called ATE. So means and has uh, at a time we test more than I think 1,000 parameter for device, and it depends on the how the test developer is wrote a program to test this device. So it takes that time. So maybe sometime 1 second, 1 second 20 device tested, or maybe 3 minute one device. It depends on the number of parameter we target to test. And this AT is also used for mass production. So when it's used for mass production, so there is no human involved. Of course, human work cannot be avoided. So we connect automatic handler in this. So human is required to load the parts inside in a tray, and then handler work is connected to the AT. Then handler transfer the devices to the AT and then keep testing and load. And the handler has a different sites inside the good bins. I would say pass or fail bins. So automatically when the device is tested, it transfer to the pass or fail bins. Um, Burn-in testing is also called biasing testing, where voltage and input signals are applied, as I mentioned before. And why it is important? Because it's fast to detect the early failures. Like ELFR, it's also called earlier lifetime failure. And preconditioning, both the test target to screen out the early failure devices, which are the poor in design, or maybe some failures. This I already covered. Uh, High temperature operating lifetime, which is also known as to check the pass fail, and uh, where we have risk potential over stress. So during the burn-in test, we also have a risk to because sometimes we have to really plan very precisely that what should be the voltages to apply on the device so that it should not be overstressed for the device. Otherwise, we overstress the device, it will fail in the beginning, which is not ideal, and which is not come from the which is also not mentioned in the data sheet. And this is the reason we see a risk in the burn-in testing. Next is failure analysis technique. As a reliability, in the reliability, failure analysis is also part of reliability, and where we test, we do the failure analysis of the part, why this device has failed. But before failing as well, we do this failure analysis to check after stress what is the condition of the device. So on the left side, on the top left, you see a package. This device size is 3 by 3 millimeter. It's a QFN type package, and it's a VI inspection pack of image. And then right of this, you see X-ray image of this same package, 3 by 3 millimeter. So inside you can see the different wires are connecting to the different pads. And with X-ray, we can see what is the target that after stress we see, okay, there is no bond wire is broken, means device survived. So the bond wire is enough strong enough. Um, and the low side, you see this a picture of a microscope where we do the visual inspections. And there are two type of X-ray failure analysis called non-destructive and destructive. So non-destructive means where we don't cut or damage any part. So the first VI and X-ray image is called non-destructive, and destructive where we really cut a part from the middle, or we really remove the package from the top with some chemical processing to check whether the device is really good condition or not. This really helps us to find the root cause and improve our processes during the production or design or choosing the right material. Uh, and this picture you see, it's a CSAM. It's called a scanning acoustic microscope. So this is the package. It's the same package, 3 by 3 millimeter, which we have seen before earlier slide. So what we are looking for here, after the temperature cycling, the package and the die are the two different material, and this can cause delamination of the package surface. So we, after this phase, we do this CSAM process where we see is there any uneven surface or not. If there is an uneven surface, means there is a fail, because then the customer will have difficulty to solder this product on the real application. And on the right hand side, you see a picture from wire pull bond shear. So this is again the same device. I just let you know these are the multiple device in this picture. So I just target only one device. So this one device is can be seen here. So from the top, you see how the critical is the design. So in the previous picture, we have seen the package on the left corner, and here we see when the package material is removed by the slowly chemical process, and we see the real device inside. And on all these 1, 2, 3, all these sides is are the connection pads. It's called bond wire. So wire pull bond shear means test where with certain force the wire is pulled to check the strength, whether it's really strong enough or not. And bond shear means we really try to cut it again to check the strength of the device or wire bond. And from the picture you can see it's really a complicated process to develop a die with really small size, because the die is developed with layer by layer with a different mask system. Uh, Reliability design, and if we talk about the reliability in design and manufacturing, so why we do the reliability test for the, and we do the reliability test to check our design is really strong enough or not. And it's very important to the first step to develop a robust device. Otherwise, if we don't do the design testing, so before reliability as well, we do the design test with some simulations to check whether device is functioning or not, or it's reliable or not. And it's also reliability is also done to check the process control, because reliability is done two ways, one on the product and one is second in the process. So why for the product, to check when we have the new product, so we need to check the product reliability. And why for the process, because we need to check, because maybe we develop one device now and in the last next 5 years again we have to develop supply this same device to the customer, but we don't know our process, maybe there is some change. So this is also important to qualify our process, that process is reliable enough to pass all the quality gates. And material layout optimization is very important, because if material is not correctly chosen, then we see a lot of failure, and this can also happen, and this can be a really big problem to the customer and the company as well. Different why material, because some time to time all the companies try to choose different material, and the reason behind it maybe to improve the quality, maybe to cut the cost down, This is the reason they try to keep testing different materials as well. And the challenges we see for the uh, development during the development during the design and all, and choosing the material and all, because shrinking the geometry is again comes from the material. Because sometimes we trace the part and maybe the die is shrinking because of some material mismatch. So this is also failed. So this is the big challenge as well. And also the challenge to qualify new material, because new material should qualify based on our requirement, otherwise we will not use it. And sometimes company need to have alternative material. So this is the reason they keep trying on the new material as well, but this is just for internal for them. Until it doesn't qualify, they do not take it for the mass production to the customer. And in the end, we also do some internal analysis, artificial or machine learning by to um, predict our reliability and to calculate our device lifetime and the functionality. Yeah. Uh, these are some standards which we follow. Mostly all the electronics or semiconductor industries, they follow this kind of standard. These are the JEDEC standards. All this type of reliability trace comes from the JEDEC. And ASEQ 100 is for automotive industry. There is slightly difference between ASE and JEDEC. JEDEC is mostly used for the consumer focus on the consumer, and ACQ 100 for automotive. And we apply this similar type of strace, but ACQ 100 we the different hours and different temperature and humidity and uh, harsher condition are applied. And ISO 26262 uh, is a safety standard, which we partially we use it. We are not that much involved in that, and in the end, we also use some internally quality standards, which help us to develop our process internally uh, and uh, to the connecting teams where we like for the product engineering team. So we comply with the same quality internal standards, that okay, this is our process. Because why this internal company standards are important? Because for example, in for during the qualification there is a fail, so we have to report it, we cannot hide it. So then higher management can ask, okay, what is your process, tell us. So for this reason we prepare our internal processes, that we say, okay, we follow all these steps. So if there is a gap, we can fulfill, or we can do what analysis on the what type of failure we have, and we can also always ready to improve this internal company standards. And time to time, you also see some change updates on the all these JEDEC and AC ISO standards as well. Uh, in the conclusion, yes, reliability is critical to achieve for semiconductor devices, um, uh, until we don't finish our final tape out. Tape out means the device is ready to launch in the market. And all the industry, same like for all the industries, we also have to work for continuous improvement. It's also essential to improve all the processes. Uh, questions? Any questions from any slide
Please
or
type
any?
in the chat box. So there is one question. Dr. Aditya Mandloy is asking,
Hmm?
which tool is demonstrate reliability and how we can perform research in semiconductor?
Could you please repeat question? Which tool?
Can you hear me, sir?
Yeah, I can hear you, but I just missed some voice.
Yeah. So this is there in the chat box. I am reading out for you. which tool
Hmm?
is suitable to demonstrate reliability and how we can perform the research in semiconductor. He's
Uh,
asking tools for reliability analysis, like you have mentioned, for example, thermal shock, maybe humidity,
mhm. Yeah,
AC,
yeah,
all these things.
yeah,
So
yeah.
which is the tool which is helpful, and he's asking whether how we can perform research in this particular area.
Yeah. So there are different aspect of this. So there is not only one tool. So one tool cannot achieve all the type of stress. As I mentioned, uh, humid HAAS is a different functionality of the equipment where we apply humidity, pressure, and pressure inside. And the same thing cannot be achieved with the HTSL. So for all the different type of stress, we use different tools. Do you want to know the name of the tool?
Yes, I think.
The machine. Okay, so for example, for Haas, there is a company called Foch. It's a big company. They develop all these different equipments for humidity as well, for temperature cycling as well. And might be in this picture, this one. You see, equipment is called EDA. It's a company. They develop dedicated for this equipment for the high temperature operating lifetime testing.
Okay,
Did I
thank you,
answer?
sir.
Did
Yeah,
I
there is
answer?
one. Aditya, sir, is it the answer to your question? Dr. Aditya Mandloy?
I think he wanted to know for the research as well, right? I guess.
Yes, yes, yes. So,
Okay, so for research, the reliability companies they do not manufacture this equipment, right? So we for the semiconductor side, okay. So his question is software testing for semiconductor. Okay, I will come back to you. Uh, so we don't develop this type of equipment. This is from third party. We provide them our requirement. So once this equipment is here in-house, then we program it based on our requirement. And about the software tool means, uh, uh, give me a second. This tool. Okay. So this uh, I would say there is a very big software behind this, and software team is working like we call them test engineers. So they develop a specified test program, software test program. It's written in the different languages, either Python or C++, mostly in C++ or Python. Um, so they in their program they target to uh, test all the parameters, like where they mention what is the minimum value, what is the maximum value, what is the typical value, and minimum of typical as well, maximum of typical. So they target so all these parameter inside. So I cannot say you that uh, which exactly the parameters or I cannot show you the software for this. It's not allowed. And for the research point of view, yes, you can, if you are working on that field, then definitely you can optimize this software as well in better way to test for the testability side for the device.
thank you so much. Sir, there is one more question.
Mhm.
Sai Kumar is asking whether one at a time or multiple at a time we can do the reliability testing.
Uh, uh, in the picture, you see only one device at a time. Left side, it's just for explanation that one device. But when the device goes for the mass production, then it is multi-site test board is there. So like, uh, where is my previous picture? This one, right? So in this picture, you see there is a HTL board. It has multiple sites. So similarly, there is another load board which has 20 side, 30 side, which is connected to this AT machine. And from this AT, it's placed on the top of the AT machine. And then from the bottom, and then AT machine is programmed. And then from the bottom, different pin is making contact to the device from the bottom of the this HTL or load board. And with this pin, they apply certain voltages, temperature to be able to test. So it depends what you want to achieve and what you are target to develop this tester, either one device, single device, multiple device.
Thank you so much, sir. So, Dr. Aditya, basically, probably you are looking for circuit level temperature and pressure conditioning and its simulation purpose. So, for that, we have TK tools like Cinturus is one of them, Silvaco is another one, COMSOL Multiphysics is also one of them. You may utilize these tools and you can simulate. I believe this answers your question. So, yes, testing and reliability, sir, he's asking whether we can do the reliability before manufacturing of the chip. This is his question, sir.
Uh, what do you mean by before manufacturing? You mean before handing over to the customer? Yes, this we have to do before tape
No,
out.
no, no,
So
no.
means.
He's asking, let us assume I have one NBT adder circuit and I just designed the RTL and
Mhm.
then I created a synthesized netlist. Can I do the reliability analysis on that? If
Now
it's
you have, yeah, now you, as I understand, now you have only design, right? So first, to test the design, there are some simulation. You have to run simulation to check all the gates or transistor are working as required or not. And then you have to, if you want to um, uh, do a manufacturing of this device. So first stage is to do a pilot manufacturing of this device. And this run is not only for tested only for one device. When the device is new, so we have to develop, we have to uh, qualify three lot. Three lot means all these three lot from the different material. Design is same, but material is different to be able to check whether it's really working for the different material or not. So based on the cost, the material is supply, the device is supplied to the customer. And three lot means each lot will have 77 parts pass. So this is also mentioned in the JEDEC that how much quantity should be tested in one lot. It's like this. So you cannot test the device before it's manufacturing. So you have to manufacture. We in the I think we can say prototype. We can say prototype. You have to develop a prototype device, then you have to test reliability.
I hope it answers your question, Dr. Aditya Mandloy. Okay, thank you, thank you. One more question is asked from Mr. Sai Kumar. This kind of reliability test, whether it is stress, temperature, environmental, are we going to do for each and every chip or randomly we are going to take? Because sometimes the chips can go in millions or trillions. So are we doing it for all or randomly with few samples?
Uh, I think I can divide in this question to two part. So for reliability point of view, as I mentioned, for example, we develop new device. So we are developing three lot. So during this three lot, we have to test all these devices. So each lot will have 77 device. So means 77 device not only for H2L. So all the strays are here. So 77 device will dedicate to HTL, 77 to LTL, 77 to THB, 77, 70, all these 77 will device, separate 77 device will be distributed in all the strays because we have to test all and we cannot test 77, wait for the 77 device that when HTL will finish, then we go for LTL. So we have to go for all. And for mass production, yes, we also have to test all the devices. And but what is the difference between reliability stress test, electrical test and mass production? The test window. So the parameter window, I would say, for example, for when we apply a voltage, so it's and the device giving output from 1 milliampere to 3 milliampere, right? And for production purpose, this output window, this current window is wider. So means it could be 0.5 milliampere to 3.5 milliampere. So the different test program is run to achieve this, because for customer uh, always relaxed uh, test window, and for quality we have to make it tight so that device should perform within specify this and pass it. Because when we when we apply this stress, so definitely parameter shifts, and then we see the outputs are shifting, and it's called drift analysis. We call the drift parameters are drifting either lower side or higher side due to the stress condition.
Okay, thank you so much, sir, for your insightful talk. Definitely, I believe all of the participants got empowered with the help of your expert lecture, sir. Thank you so much for your time
Yeah,
and your support, sir. Thank you, sir.
yeah.
Let
Thank
us
you, thank
conclude the
you.
session.
Yeah,
Okay, sir.
thank you.
Thank you so much.
Bye bye.
Bye, sir.
Bye bye.
So, thank you, everyone.